Welcome. This presentation introduces confidential service meshing using Intel SGX and the SCOAN platform for confidential computing. With the increasing popularity of cloud-native applications, we have also seen an increase in the popularity of service meshes. A service mesh facilitates the communication between services or microservices. This service-to-service communication is often facilitated with the help of a proxy. Examples of frameworks supporting service meshes are Istio or Spire. In general, these services use a proxy to facilitate the communication. This will, however, break the end-to-end encryption of the communication channels. As we explain, these might result in some of the traffic being accessible in plain text. In what follows, we first explain the advantages of service meshes. We introduce a confidential service mesh which ensures end-to-end encryption with mutual authentication. This implies a mutual attestation of the services. We assume that you already know about cloud-native applications and confidential computing. We recommend to watch our presentation of confidential cloud-native applications to learn more about confidential cloud-native applications. A cloud-native application consists of a set of services or microservices. We use the term service to refer to both the microservice as well as general service. A modern service is typically providing a REST API to other services and clients. A REST API uses TCP as a reliable transport protocol. On top of TCP, there is HTTP that provides a set of methods or sometimes also called verbs. These verbs can be used to create, read, update, or delete a resource. Different services will provide access to different resources. A resource might be a blob, meaning a sequence of bytes, or a key-value pair. A service might have one or more endpoints, meaning REST APIs. In this example, the service B provides a REST API to which service A connects. It provides a second REST API to services C and D. Service meshes permit to connect these services with mutual TLS. A service mesh ensures the confidentiality and integrity of the data in transit. This is achieved with TLS. This is a protocol to encrypt the traffic of a network channel. There are two pairs of a channel, one is the service end and one is the client. In this example, service A would be a TLS client connecting to service B in TLS. The client always authenticates the service. This means that the client verifies the identity of the service. This authentication is performed with the help of certificates. Service meshes use a variant of TLS which is called mutual TLS or just MTLS. This is a method for mutual authentication. Both parties of a MTLS connection need to authenticate themselves. The service as well as the client need to provide a certificate to the peer. Each certificate includes a public key. Each public key is associated with a private key. The private key, as the name indicates, is kept secret by the peer. The peer can authenticate itself by proving that it knows the private key. TLS verifies that the peer knows the private key, without revealing the private key. We need to control the access to APIs. Not every client should have access to a service. Moreover, clients need to verify if a service is indeed authorized to provide this service. We need to ensure some access control that can be enforced by the owner of an application. We show how to control access to an API with the help of certificates. To do so, we need to introduce some basic technical details first. A certificate includes a signature to ensure that the certificate was not modified. A certification authority, or short CA, signs certificates. Each CA itself is associated with the CA certificates. A CA certificate is either self-signed or signed by another CA. One can use the CA certificate to verify the signature of a certificate. In other words, one can check if the certificate was indeed issued by a certain CA, and TLS ensures that the peer knows the private key belonging to the certificate. This means that we can use certificates for access control. Only if the client has a certificate from the right client CA and knows the private key, it can establish a TLS connection with the service. A client only establishes a TLS connection with the service if the service has a certificate from the right service CA and it knows the private key. To give clients access to a service, we need to define who are authorized clients and give only these clients access to client certificates include a private key each. To grant a service permission to serve a certain API, we need to define which service instances are authorized and grant these service instances access to service certificates including a private key. Current implementations of service meshes use proxies to implement the MTLS between services. In Kubernetes clusters, the proxy is implemented by a sidecar. This is a container that executes in the same pod. A pod can be viewed as a logical server. The containers in the same pod can communicate via local, socket-based communication, and they share the same network to communicate with other services. By using a proxy, has several advantages. One can configure the communication in a generic fashion, that is, one does not need to figure out how to configure TLS for each individual service. Moreover, one can monitor the traffic between services in a generic fashion. Regarding confidential services, this has the disadvantage that the communication is not end-to-end encrypted between the client and the service. There are always two proxies between the confidential client and the confidential service. Moreover, the operating system and hence, all root users that have access to the pod, can capture the traffic. This means that unauthorized users and software components might be able to intercept the traffic in the clear. Let us show how we can turn our service mesh into a confidential service mesh. This service mesh consists of confidential services, that is, they execute inside of Intel SGX enclave such that all data in main memory is encrypted, all data at rest is encrypted, and in particular, all data in transit is encrypted. We run each service inside an Intel SGX enclave. This enclave resides in an encrypted region of the memory. Only the software executing in this memory region can see the unencrypted memory. No hardware device nor any other code can read or modify the content of this memory region. Note that Intel SGX is the only technology on the market that permits to protect individual services. The SCOAN platform enables unmodified services to run inside of SGX enclaves. It transforms the container image such that a service is automatically started inside of an SGX enclave. The SCOAN runtime is part of the enclave. The runtime can transparently encrypt the files that a service writes. Moreover, SCOAN includes a network shield which can transparently encrypt network traffic. It can also restrict the network traffic of a service. We can use SCOAN in at least two ways to build a confidential service mesh. First, we can extend existing service meshes to ensure that the network traffic is always encrypted. This provides more features that come with common service mesh implementations like Spire. One can monitor the traffic and perform network diagnosis. One disadvantage of this approach is that one increases the complexity and we need to ensure that all components are indeed being protected. For example, we would need to ensure that there is no functionality to inspect the network traffic in the clear. Second, we use the SCOAN network shield to build our confidential service mesh. This permits a precise approach for access control access to the APIs. Moreover, we can ensure that the mutual authentication translates to a mutual attestation. We come back to this point in a few slides. Let us first focus briefly on alternative 1. We want to ensure that all communication is always encrypted. With the help of SCOAN, one can transparently encrypt network traffic. To do so, one describes in the security policy of a service and the proxy that the traffic between the service and its proxy is transparently encrypted by the SCOAN network shield. In this way, nobody can read the traffic in plain text. Also, any modifications of the traffic by an adversary are detected. The services and the proxies are all executed inside of enclaves. In this way, all data, code and secrets are protected. This means that an adversary cannot read or modify services or proxies while executing. The advantage of this approach is that one can use the full functionality of service mesh frameworks like Spire. The disadvantage is that we have 3 instead of only 1 MTLS connection. This increases the overhead. Moreover, we execute 4 instead of only 2 enclaves. Moreover, the proxy needs additional configuration to set up. We have experience in setting up the confidential service networks. Please send us an email if you need help. Alternative 2 uses the SCOAN network shield to establish MTLS connections between the services. The network shield is part of the SCOAN runtime. This means that it runs inside the enclave together with the service. There is no need for an extra enclave for a proxy. Moreover, there is only one instead of 3 MTLS connection needed between the client and the service. The SCOAN Network Shield can establish the MTLS connection on behalf of a service. Network connections are automatically wrapped inside of a TLS connection. The Network Shield limits the accepted client as well as service certificates. This is configured as part of the security policy of a service. We show a little bit later on how to do this. With SCOAN and its Network Shield, we can build confidential cloud-native applications consisting of confidential services, that is, these services run inside of Intel SGX enclaves. All communication is automatically protected via MTLS. In this way, we can protect all data and code and secrets in use, in transit and also at rest. Let us look at some technical details to investigate the security and access control that we can achieve by defining a policy for each service. To set up a mutual TLS connection, the Network Shield requires some arguments. First, a client needs the CA certificate of the service that the client is connecting with. This is used by the Network Shield of the client to ensure that the service has the right certificate. Moreover, the client needs a client certificate and the corresponding private key to be able to authenticate itself to the service. Similarly, the Network Shield of the service needs a client CA certificate to be able to check if the client is authorized to use this API. Moreover, the service needs a service certificate and a private key to ensure that no service can impersonate another service or impersonate another client. We need to provision these information in a confidential fashion to the service. To configure the Network Shield, we need to provide the enclave with arguments, but we also need to ensure that these arguments are not leaked. To do so, we define these secrets inside of a security policy. The security policy is protected and enforced by a SCOAN service that we call SCOAN CAS or SCOAN Configuration and Attestation Service. The policy defines how to attest and verify a service, meaning, on how to make sure that only an authorized service can get access to the secrets. The standard way to attest and verify a service is to specify a secure hash value. Intel SGX creates a secure hash value during creation of the enclave, and SCOAN CAS verifies that this matches one of the specified hash values. Moreover, SCOAN CAS verifies that the CPU has up-to-date firmware and hardware. After a successful attestation and verification, SCOAN CAS provisions the secrets to the service. In this case, it would pass the arguments that the Network Shield requires. SCOAN policies permit to define certification authorities as part of a security policy. In this example, we define a certification authority called Client CA for client certificates as part of the CA policy. The certificate of this CA is exported to the service policy. The service policy imports it and would use it in the configuration of the Network Shield. The CA certificate also generates a client certificate with the help of the client CA. It exports the client certificate to the client policy. The client policy imports it, and hence, it can use the client cert in the configuration of its Network Shield. Similarly, one would generate private public key pairs in one session and export and import in another session. Note that the policy can be located on different SCOAN CAS instances. This means that one can share secrets across multiple administrative domains as long as both sides agree. That is, one side exports the secret and the other wants to import the secret. Mutual TLS can be used as an implicit way that services attest each other. In the example from the last slide, we define a CA policy that defines the CA and client certificates. The same can be done for the service certificates. The policies are connected via imports and exports. In this way, they agree on the same CAs for the client and service certificates. The MTLS connection can only be established if both pairs got all their certificates and private keys that are specified in their respective policy. This means that this connection can only be established if both pairs passed their attestation and verification. In other words, the mutual authentication of MTLS implies a successful attestation. The Network Shield permits to enable MTLS in a generic way. Most applications support TLS or MTLS2. One can generate the certificates and private keys in the same way as we sketched above. Sometimes is the TLS stack of a service not that easy to configure. Often, this requires some application-specific knowledge. With the Network Shield, one can configure the stack in the same way for all applications. If one is familiar with the configuration of the TLS stack of the application, one might want to use this application-level TLS. If one is not that familiar, one might want to use the Network Shield and configure the application without TLS. In some cases, it might make sense to enable the application TLS and the Network Shield. This means that one has two nested TLS connections. Let us first look at an example of how to configure the TLS stack of an application before we get back to the nested TLS connections. MariaDB is a popular SQL database that shares some common history with MySQL. We can enable TLS in the configuration file of MariaDB. We can also enable MTLS in the configuration file. That is, we can require that a client needs to authenticate itself with a client certificate. The default configuration file of MariaDB is myCNF. In this file, we can enable TLS and specify the files for the server certificate and the server private key. Note that both the configuration file myconf as well as the server certificate and server private files need to be protected. Scone permits to inject files into the file system of a service that executes inside an Intel SGX enclave. This means that the file is not visible outside of the enclave. The content of these injected files are defined as part of the Scone policy of the service. Let's have a closer look. This slide shows an extract of a Scone policy for MariaDB. This policy is stored and enforced by SconeCAS. We instruct SconeCAS to generate private keys, a CA certificate, and then generate certificates with the CA. Since we showed that already before, we skipped most of the details on this slide. Instead, we focus on how to provide these secrets to the application. We define some injected files in the images section of the Scone policy of MariaDB. We inject the MariaDB configuration file at path etc. myCNF. This configuration file contains the path of the server certificate, the server key and a few more files like the CA certificate used to generate the server certificate. The certificate file contains the certificate MariaDB that is defined in the secret section. The private key contains the private key that is also defined in the secret section. In this way, we can enable MTLS for MariaDB. In some cases, service might only support TLS but not MTLS. In these cases, one should probably use the Network Shield instead. One can use the Network Shield not only to connect services of the same application but also different applications. The approach is similar to connecting service of the same application. Let us look at a very simple example. We have two applications that are operated by two application owners. They might run in the same or in different clouds. Let us assume that both applications are confidential applications running inside of Intel SGX enclaves and running with the SconeCAS policy. At least the services that connect between the applications would need to be confidential in this example. Each application owner might use a different SconeCAS. In this example, App 1 used the blue policy on the left, SconeCAS App 2 uses the green policy and the right SconeCAS. Despite using policies maintained by two different CAS instances, one can share keys. In this way, one can establish MTLS connections between applications hosted in different clouds and using different SconeCAS instances. Note that this replaces the typical root CAs. The motivation for this might be to limit the external dependencies to root CAs. For example, to avoid potential man-in-the-middle attacks via a malicious root CA. One of the problems that we need to address when connecting two applications in different clouds is that we have firewalls. Security policies might require that all connections are terminated at the firewall. This means that we do not have an end-to-end mutual TLS. Hence, we do not have mutual attestation of the two peer services either. One approach to address this problem is to enable the Network Shield in the application TLS. The Network Shield encapsulates all traffic by the application in a TLS connection. In this case, this traffic would itself be a TLS connection. In other words, We have two nested TLS connections. The outer TLS connection has the client credentials of the network shield and the inner TLS connection has the client credentials of the application. Using the two nested TLS connections, to connect to a service behind a firewall, we can ensure an end-to-end MTLS and hence, also a mutual attestation of the two services. The outer TLS connection of the client is terminated in the firewall. The firewall would in this case check if the client is authorized to connect to the service. Note that by checking the client certificate, the firewall would implicitly attest the client. It would also check if that client is still allowed to connect to the service. If this is the case, the firewall would forward the inner TLS connection to the service. The service would terminate the connection. The service could use the network shield or the application logic to do so. In any case, the service would perform a mutual authentication and hence, also a mutual attestation. Now, let's look at a demo that shows how to use the SCO Network Shield.
Hello. On this video we're going to talk about the Network Shield feature of the SCOAN runtime. With the Network Shield you're able to transparently encrypt all the network communication that's performed by your application running inside of Intel SGX Enclave. So with that, you're able to implement TLS or mutual TLS to your application without the need to change the code, because this is all done via policy, right? And not only that, but also the information that's used to authenticate that connection, the certificate and the key, they only exist inside of the enclave. So you know that you have this end-to-end protection, because you know that the communication is going to be terminated, the TLS is going to be terminated only inside of an Intel SGX Enclave. So this is quite common, especially in the cloud-native world. You have service meshes that have proxies that usually implement that for you, so that transparent encryption of the network communication, and they implement mutual TLS, but that's not entirely end-to-end because the last leg of the communication, which is between the proxy and the application itself, is usually not protected. So with the Network Shield, you have this ability to do that securely because everything is inside of the enclave. All right. And not only that, the Network Shield also functions as an application firewall, as I'm going to show later on, right? So to showcase this feature, we have a Kubernetes cluster running here, and we have three things on it. So we have our server, which uses a Redis instance for persistence, and the server, it's exposing an API for patient records. So it's on the eHealth domain. And we have also a client that keeps creating patient records, right? As you see here, the logs for both. So we have the server getting requests and the client creating new patient records. And as you can see, the records, they contain a lot of sensitive and private information. So we want to protect that, especially when running on the cloud, right? So here, those three things, so the server, the client, and the network, and the Redis, they already run on SCOAN, and they have remote attestation turned on. So they already have data in use protection because of the Intel SGX enclaves and the encrypted memory. They also have data at rest protection because the SCOAN runtime transparently encrypts the file system. So for example, if I am a Kubernetes admin that I have access to this, to the pods here, and I want to check, for example, the code for our server, I could see the Python file that has the server here, which is restapi.py. However, it's everything encrypted because only the Python interpreter, after it's attested, so we know for sure it was not modified, it's the one we trust, only after that it gets the keys to actually decrypt this, and this is done transparently by the SCOAN runtime. So the applications, they don't need to know about encryption to benefit from that. So yeah, however, if we look in here on my machine, I'm going to show the actual code for the server. It's just serving a plain text HTTP. So there's no TLS setup going on. So the server and the client, they talk over HTTP, so it's just plain text communication, so that's not secure. For the server in Redis, since Redis supports TLS natively since version 6, we use TLS to communicate to Redis. So server in Redis, they already talk TLS, and the certificates here, they are injected by this SCOAN runtime as well, so they only exist inside of the enclave, right? But for the client server communication, that is done out in the open, and we can we can illustrate that by also coming back to the admin example. Suppose I'm an admin with access to this cluster and this pod, so I could run a TCP dump here and see how the communication looks like between the server and the client. So as soon as we start to see some traffic here, we can start to see some plain text information here. For example, this is a score for a patient, and this is the ID of the patient. So that's sensitive, that shouldn't be here. I shouldn't, as a Kubernetes admin, I shouldn't be able to see that stuff going over the network, right? So if we continue to scroll here, we can see a whole patient record. So all the sensitive data here, pre-existing conditions or insurance details, social security numbers, and so on. So everything is here out in the open. So even though we have data in use protection, data at rest protection, data in transit protection is not in place yet. So the idea here is to showcase how to enable that using the SCOAN Network Shield, right? So as I mentioned, the services already have policies, and the Network Shield is only configured through policies, so you don't need to change the code for the client or the server. So let me show the policies for both client and server, right? So the idea here, note that the server policy is called Network Shield Demo Server, and the client policy is called Network Shield Demo Client. This is important when we start to sort of exchange information between the two. So to set up the Network Shield, I just need a couple environment variables. So let's start with the server here. So I'm creating a new section here called environment, and here we define secure environment variables, right? So let me go ahead and paste some Network Shield related environment variables here. So this is basically configuring the Network Shield. So they all start with SCOAN Network Shield. And here I'm configuring a server port because this is the server policy. So here I set it to protected. It could be, I'm calling this server 1, but I could have as many as I want. And this port here, I'm configured to protected, so it means that all the communication must be according to the parameters that I specify here. I could set it to unprotected, which means we don't filter the communication, and we could set to refuse, in which case the application wouldn't be able to bind the port. So that's where we can start to limit how our application talks to through the network. So that's the application firewall sort of feature that we have also. So to configure this, I configure a server port, which is TCP 4996, which is the API port. I have an identity here. I have to specify the identity for the server. So here I would specify my key and my certificate for the server. So I could paste it here. But since we are using SCOAN, I'm going to generate them securely inside of the enclave. So no one will ever know the contents of the key and certificate, right? So, all right, so yeah, and for client authentication, I'm setting to disabled for now. If I wanted sort of the mutual TLS going on, I would specify some client CA here to authenticate the clients that come in. So as I said, I'm not going to paste client a key and a certificate here. I'm going to generate them through SCOAN. So for that, I'm going to extend our secret session here, where we specify our secrets. Currently, it only has this Redis related certificates and keys that we need, right? So we are going to extend that to include a few more things. So I'm going to put this things here. So I pasted a few lines here, and what those lines are doing is basically first we're creating a CA key, and then creating a CA certificate. You notice by the kind, which is X509 CA. We are also exporting the CA for the Network Shield demo client policy, which is this one here on the right. And we are creating our server key and our server certificate. Note that we are creating an endpoint, a server endpoint certificate, and it's issued by CA, which is a reference to the CA we just created here. So, additionally, we also set up some subject alternative names that we use. So since the clients are contacting this API through a Kubernetes service, we just put the name of the service here, which is API server, right? And moreover, we are also importing the client CA from the client policy, which is this one. It still didn't create those secrets there, but we're going to get there. So now that I created my server secrets, I can finish this setup here. So for the server identity, I'm going to use the secrets that I just created. So I'm going to use the server, and then I have the private key. So depending on the type of the secret, so for example, this one is X509, you get some fields that you can access like this, and this --scone syntax is to reference the value of a secret. So I'm essentially referencing the value of server. And in server, since it's an X509 certificate secret, I can access its private key through this property here. So I'm getting the key, and I'm also getting the certificate here. So this is basically putting the content here, although I won't be able to see it because it's generated inside of the enclave. And since we have the client CA already, I'm going to also set up its certificate here. So it means that I only accept clients that were issued, the certificates were issued by this CA here. So this completes the setup for the server. So we now jump to the client to also do the same. So as I said, I just need a couple environment variables to set up the Network Shield for the client. And we can sort of paste them here. All right, so yeah, so we have the same thing. So now since it's a client, it's connecting to some destination. We create a client destination. So this one is called 1. So we have client 1. We could have as many as we wanted. So yeah, the destination here is TCP API server, which is the DNS we're connecting to, and the ports. Of course, I'm setting this to protect it because I want the connections to be according to the parameters I define here. If I set to refuse, then the client wouldn't be able to contact this destination. So that's the firewall application, the application firewall, right? So for IP, since we are on Kubernetes and the pod IP is not very used, to be honest, so we just set it to a wildcard. So anything will match here. And then we set our client identity, and here we do similarly to the server. We set the private key and the certificate for the client, and for the server authentication, the same thing, the CA for the server. So let's use secrets here to do that. So yeah, so I'm pasting this here. So same thing, I'm creating a CA key in a client CA, which is now exported to the server policy, which is this one. So this allows this one to access this client CA. Then create a client key and a certificate, pretty much the same thing. And then the server CA we import from the server policy, so we can reference it here when we set up the server authentication. We can do it right now to here. So yeah, so since we have the server CA here, we can just server CA cert, and now we are authenticating the server. It must be the certificate must be issued by this CA here. And for the identity, we do something similar. So we have our client and then private key, and we have our client certificate, right? So that's it. So with those changes, we now set up the mutual TLS between client and server. That's transparently enforced by this Scone runtime. So let's save and apply those changes. Yeah, so Scone session update server, Scone session update client, right? So now that the policies were updated, we go back to our cluster, right? And I have to restart the pods for the changes to take place. So I'm going to keep watching the logs for the client here. And I'm going to now restart the server just to see what happens. So I'm going to delete the pod. Remember that when the pod restarts, it's now going to pick up the new configuration. So it's going to serve TLS transparently, even though I didn't change the image or the code. So you see that reflects immediately on the client, which does not expect the server to be TLS, because I didn't restart it yet. So it's still using the old configuration. And now it cannot connect anymore because it does not know what's happening, because it's now TLS. So to fix that, I have to restart the client at 2. So let's restart the client, and then when the new client starts, it's going to pick up the new configuration. So you see that when I see the logs, then now the communication is established again. So that's the Network Shield transparently encrypting the communication between the two services. And if I go back to the scenario where I am an admin that wants to sniff the traffic here, I can run the TCP dump again. And you're going to see the traffic, but now the difference that the traffic should be encrypted, because the Network Shield is doing that for the application. So you see that I cannot retrieve any meaningful information for the data that's being communicated here. So that's the goal for the Network Shield. And also just to showcase the application firewall capabilities. So this is now set up with MTLS, but suppose I could also do this. So I could go to the server policy, and suppose I want to have complete control of the communications for the server. I could, for example, sort of set the general Network Shield policy to protected. So by default it's unprotected, which means that the Network Shield only filters the connections that are described here, and the other ones it just don't do anything. But if you set to protected, you're like in a strict mode, sort of a denial, and you have to explicitly add all the connections that your application is allowed to do. So if I do that, I'm sort of switching the server now to this strict mode, so it's only able to serve on this port here, and that's it. So if any other type of communication tries to take place, it's going to be denied by the cluster, so by the policy. So let's just update this one real quickly. Okay, so now the server is in this new mode, so let's restart to see the changes take place. Okay, new server is here. Let's see the logs for the new server. You see that now the new server just crashed because, of course, we just allowed it to serve, but we didn't think about Redis. So it's trying to connect to Redis, but since there was no explicitly client destination there for Redis, it just didn't allow the communication to happen, and then the server crashed. So to fix that, I would go there and add a client destination to Redis. So that's the application firewall, and this wraps up the demo that I wanted to show you. So thank you very much for your time. I hope you enjoyed it, and see you in the next one. Thank you.
If you have any questions regarding confidential computing, SGX, or the Scone platform, please feel free to contact us at info@scontain.com. The technical documentation of Scone is available at sconedocs.github.io. The commercial website of Scontain is available at scontain.com.